the light out into a little rainbow and then measure how much light there is at each color, how much blue light, how much green light, how much red light, on into the infrared. We can measure from the light emitted by the galaxy whether it's coming toward us or away from us and how fast. So we're all familiar with that effect. When you hear a car zooming by on the highway, you know that it makes this sort of sound. It goes from a kind of high pitch to a low pitch as it goes past you. The same kind of thing happens with light. A galaxy that's approaching us has its light shifted to a higher frequency. That means to the blue a little bit. And a galaxy that's moving away from us has its light shifted to the red.
By analyzing the color of galaxies, Kirshner can estimate their distance from the Earth. In the 1920s, astronomers discovered the universe is expanding. Most galaxies are moving away from us, and the farther they are, the faster they move. Therefore, a distant galaxy will have a high red shift, and a nearby galaxy will have a low one. Kirshner and his colleagues have measured the red shift of about 25,000 galaxies observed in narrow windows of the night sky. Their data forms a three-dimensional map. At the center is the Earth. The edge is 3 billion light years away. In some areas, galaxies cluster together. Other regions are dark and empty. Like mountains and valleys, these are important features of the cosmic landscape, but small details in a map that shows a tiny slice of the universe.
The neighborhood is very complicated, but that's just the local detail. We have to go pretty far out. Just as if you were mapping on the surface of the Earth, you'd have to go pretty far away before you'd see the effects of curvature. In the same way, we have to go not 800 miles, but 5 billion light years to begin to get really significant effects that we might be able to measure. And the tool that we use is the apparent brightness of exploding stars. The exploding stars are very bright. For a period of about a month, one of these things is as bright as 1 billion stars like the sun. The stars exploded 5 billion years ago. The Earth is only about 4.5 billion years old. That means these stars exploded before the Earth even formed. So while the light was on its way, the Earth formed, life began on Earth. Here we are, we built the telescopes, we got up to the top of the mountain, and we're able to see it just as the light arrives on some particular night.
These stars are called supernovae, and when they explode, Kirshner can measure their brightness. From their color, he can also measure their distance.
To look at the relation between distance and brightness of supernovae. You can imagine what that would be like in flat space, that as you go farther out, the things you see get dimmer and dimmer. The brightness goes down like the square of the distance.
The inverse square law tells us that lights of similar brightness will be 1/4 as bright when they are twice as far away.
But if we see some deviation from that in the brightness of these things as we look at them at bigger distances, that means that the underlying geometry is different.
In nearby galaxies, Kirshner has measured exploding stars and plotted the results on a graph. If the brightness of far-flung supernovae is the square of their distance, then the universe is flat. If it is not, it must mean the shape of the universe is curved in some way. To answer the question, Kirshner and his colleagues must collect light from exploding stars far across the universe, pushing the most powerful telescopes to the limit. searching the night sky, Robert Kirshner waits patiently to measure faint traces of ancient light.
I think we're really on the path here, unless there's some joker in the deck that we haven't come across yet. I think that in the space of a couple of years, we'll have at least a preliminary answer to the question of what is the geometry of space. Some people think they already know, but we're engaged in this tremendous adventure of trying to measure it. We're sort of at the stage of the Greeks understanding the shape of the Earth. And that's because we're working on things that are really at the limit of technology today.
An astronomer explores a fundamental question about the physical universe. The invisible universe of mathematics allows him not only to calculate the answer, but to imagine the question in the first place.
All the centuries of progress with mapping the Earth and with the mathematics associated with it allows us to think about mapping the universe and understanding the pictures that we come up with. You look out there, you see these galaxies, different distances, different directions, but you can't put them all together without the geometry to analyze what it is that you're seeing.
The geometry of curved space, now used to model the heavens, was developed in the 1850s by George Frederick Riemann as a result of measuring the curvature of the Earth.
The Greeks were the first to realize the Earth is not flat. And Riemann sort of did the equivalent thing for space. He said, well, possibly all of space is a three-dimensional version of the spherical shape of the Earth, which is the two-dimensional surface, and he wrote down an equation.
Calling Riemann a genius, Einstein used his geometric equation 75 years later to explain his theory of relativity.
The big contribution of Einstein was to basically equate Riemann's geometry of space with the physics of the universe, so that all of 20th century cosmology really grew out of Riemann's idea of higher dimensional curved spaces. Understanding these geometric properties continues to this day.
Look at those beautiful tulips!
All right. Neat. You have a nice garden here. We're born into the world. Everything's a surprise to us. We go out, we want to see what's there. And asking about the shape of space is just asking about this largest scale, saying what's the playground that we find ourselves in here? What's the shape of the whole thing? That was special.
In the physical universe, curved space is a possibility. But in the mathematical universe, it is very much a reality. And Jeff Weeks has devoted his life to exploring it.
Even though this quest for understanding the shape of space is a relatively new question, it's part of an intellectual tradition that goes back thousands of years to the Greeks. Our mathematics is, in a sense, spacemetry instead of geometry. Rather than just measuring the Earth, we're now going and measuring